to another video. In this video I'm going to talk about some advanced railgun theory and some extra design theory. But first you might be wondering where I've been and what I'm doing. Well, to be fair, I haven't done anything lately. I don't have much content to show you yet, but that's going to change, I hope. So you might be expecting more. This video is one example, because like 2 days ago I got an idea about Railgun designs, and that's what I am going to talk about in this video. So let's first of all take a look at what you would usually model the railgun as in a form of component, which is a resistor, obviously. So we have a voltage source, which could be a capacitor or anything, and the first thing we will find in a capacitor, for example, is the resistance of the capacitor itself, which is the ESR, equivalent series resistance. And up next will be cables and such, and we will model that as a whole, as rail 1 resistance. Then it flows through the projectile, which has a resistance, and then it comes back via the second rail as resistance. Let me put this a better spot. So what we have here is then the system resistance, as we would say. The system resistance is then the sum of all the resistance components in the system. So, and that would be everything summed up, and we can model that as a single resistance and that's what we would usually model our railgun with. But I'm going to show you why this is very wrong to do. So this is wrong. This is also wrong. But for the sake of it, we are going to give it a value, let's say 6 milliohms, and let's see what this is going to give us if we put it in a RC circuit. So this would be the capacitor bank, and this would be the series of system resistance, and current will flow through here, which would then be a pretty logical model, if you think about it, because that's usually what it is. But let's make this into a real calculation, and I'm not going to explain it through. I'm just gonna let it play and see what I'm doing. So as you saw, is that the voltage is a function of time, which is the initial voltage. Euler, pretty sure you know, dE, and a tau. Tau is the RC constant. It's a time constant, so this is in seconds, which this whole thing is basically a ratio, because voltage is voltage, and this is basically not a unit of any sort. But let's see what this is going to give us. Because this is an Euler curve, or well, it's inverse, we will get something like this, or more realistic, we will get something like this, depending on your parameters. This is the initial voltage, and this is somewhere between 3 time constants, so that's just this times 3, and it will usually be in the very low second count. So if I'm going to plug in my numbers, which I had, and that was 6 milliohms, I think. This is R, and C is then 24 millifarads. Let's see what that will give us. This is a 124, 144, E minus 6 seconds, I think. Should be right. Yeah, I think it's right. So this is in the microseconds, 144 microseconds, and that times 3 is basically 4.3 minus 4 seconds, which is almost nothing. It's 0.4 milliseconds. And let's see what happens if we put this circuit in a spice model. So this is LT Spice. Pretty sure you've seen it a couple of times in my videos, but I'm going to quickly model the circuit that we just made and see what kind of results it will give. Alright, so now we have the working equivalent circuit of what we had. We're starting with 400 volt over here, capacitor voltage, which then gets discharged when the projectile enters to approximately 0 volts. And let's see what we calculated to be. We said 0.3, I'm not sure what I wrote, 4.3, 0.43 milliseconds. Let's see if I'm at least a little bit right, because it can be very different in a spice model. So let's see, 1, and approximately here to 0 volts. I'm not sure if I can reach it. So I'm about off here, which is order of magnitude of 10 next to what I thought it would be. I'm not sure if there's any stray resistance over here. Let's see if the values I used were correctly. Okay, everything is correct as what I said it would be, except this is a SPICE model, which is actually more accurate than my calculations. As you can see, it takes a little bit longer. It takes about it takes about 3.25 milliseconds to discharge to 2 volts, and we can see in this current graph that we have 66.66 kiloamps, which is what I would calculate. I think I have said it before. So that calculation is pretty accurate. And of course the 3 time constant was just a approximation of what I thought it would be, or what comes close at least. So let's take a look at this graph. This is a very important graph to understand, so you can understand what's wrong. So let me put this over here. Let's put this over here. I'm going to show you the slope. It's a very bad slope. So as you can see, if I zoom in a little bit more, zoom in even more, zoom very close. So right here, you can see why this is not a representation of what is going to happen at all. This is a time difference of 6 femtoseconds and a slope of, I'm not even sure what number that is. Let me Google it. Alright. That is 0.1 exoamps, or 100 petaamps, about 100 petaamps per second, which is not realistic at all. You might see, you might know a component which resists this value, and what we are missing in our model, and why I said that the resistance model alone is not an accurate model at all. And of course I am talking about the inductor, which will resist change in current. Note that it will resist the change in current, and it will not resist the current, because that is a resistor. And it will only slow down this slope over here, because this is just a straight line. It's just 9 degrees, and nature doesn't have straight angles. Even if you think about it, when have you ever seen a straight angle in nature? And that's what we are going to design this railgun based on. No straight angles at all, because such thing doesn't exist. It isn't normal and it is weak for a reason. So let me show you what happens when I add an inductor. So as I said, there is an inductor in this simple capacitor resistor circuit, and we saw that this is wrong. Oh well, this is wrong, and as I said, it needs an inductor. But where does that inductor come from? Well, it's pretty simple, because everything in this world has a inductance. Your hands, you, a rock, even a rock has inductance, same as it does as for capacitance and resistance. It may not be much, but it's still existing. So that's basically what you can remember, that everything has an inductance, everything has a resistance, everything has a capacitance. So everything has a resistance, everything has an inductance, and everything has a capacitance. And this, as you can see, forms an RLC circuit. We have a capacitor, we have an inductor, and we have a resistance. This is the system resistance, system inductance, and the capacitance. Now, you might think, where does the straight inductance come from? Well, as I said, we are using very big capacitance, 24 millifarads, which is a capacitance that would be in the rails, in the projectile and stuff, would almost be negligible, because this value is so high. It would add nothing to it, but as we have no inductors put into the circuit ourselves, or any resistance, it's still there, and it's a little bit. It's a very little bit, but you can see how significant that is. Now, of course, there will be a current flow. And as I did for this one, for the RC circuit, which would be this divided by R, would give basically the current slope, or well, not the slope at all, but this slope. This is not accounted for, and we will account this in this circuit with the inductance. And I'm not going to derive the current in this. I could try at least, but it's going to be a very long time, and I know what it's kind of going to look like. So it is a circuit that looks like this. Oh well, its equation looks like this. It's a second order differential equation, and this basically will turn into a imaginary equation, as I will parameterize dy dt, which will give me a quadratic equation, and that will, I'm forgetting the R, which will give me P, which stands for dy dt, the change in current, which will be a function that looks like this. Like this. Because this is 1 over c. And you can maybe already see what happens when this number gets filled in. Let's say that we have 1/24. This becomes 1 over 24, and this is a very small number, which is about 1, I would guess, or 0, I mean, minus r squared, and there are two options which can come out of it, which is a real number or imaginary. And basically what this means is that we will get a function of current that will look like this. It's a constant, Euler, and then plus minus a imaginary number, something like this. And this can be done with the Maclaurin series. Let me clear this up, which will give the whole thing with the case and stuff. It will come into play as the cosine of x plus the imaginary sine of x. So this is the complex, and over here we have the real part of the equation. So this is basically 1 and this is 1. And we will see that when everything is filled out, which takes a long time, because we need to know the constants and such, but I don't know the real values yet, but I can approximate it. But really it comes down to the function of the current being equal to a constant that's a function of the sine of omega t. So that is so that will look like a sine function. I'm not very good at drawing sine functions, but of course this is an oscillation. This is an oscillator circuit, and oscillations, they're basically resonant circuits, And any mechanical engineer will know that resonance has a lot to do with springs, and you can have either overdamped resonance, you can have underdamped, and you can have critically damped. And what this means is, overdamped you will have something like this, underdamped you will have something like this, and critically damped you will have something like this. So you can see the difference here. This is still an oscillation, this is too tight, and this is just right. So you in this circuit, you rather want to have overdamped than underdamped, which is a fact. And this omega over here can be derived from, let me think, it's derived from the same equation. If you basically solve what I did before, which brings P equals minus R plus minus R squared minus 4 LC over 2L, and if I can substitute this, well, the R in this part, this becomes then, let me think, let's call it alpha R over 2L, and omega over here, omega naught, which is actually this whole part. Let me clean this a little bit. And we are getting to overdamped and underdamped very quickly. Oops. So this becomes 4 LC yes, okay, so this gets to alpha plus minus the square root of alpha squared minus omega naught, and basically what this will become is, oops, I already have there, is 1 over LC. Right, this is not right, because it's missing the 2L and the square, so this is right. It's just basically this part. So this, you know this probably from the resonance frequency. And this is also used in the function for the current, which will define the slope of the circuit, but also what it does not define is the rest. So this is when t is less than or equal to t, where v is max, or I mean not v, I is max, and this is for when t is greater than t is max. So what is this? We will find out. So as all the current from the capacitor dumps into the inductor, it stores a magnetic field, of course. That's how railguns work. You get the B field, and what happens then is that this is going to discharge. This inductor will then form a circuit with the resistance, and this will be the voltage source. And of course we all know this circuit. Here comes. Let me make that a small I to make it. And of course this again can be solved, and it will give a similar function which will look like this. This is not a C, this is an L. So we have seen this form before, which is a, again, first order separable differential equation. And IO is the simple form of, let me think if I remember correctly, it's about the included with the capacitive discharge that's over here, that was still discharging into the inductor. So IO is V0 times the square root of C over L, and that completes the function for I after the P current curve as V0 square root C over L e to the power of minus R over L t. This should describe a curve like this if it's overdamped or critically damped, because it can also form a very oscillative resonant discharge. So you must design this properly for this to occur rather than an oscillation. And the way to figure this out is to make there is a model for damped oscillations. That's the alpha and the omega that form a ratio, and maybe I can put it off the internet. Yeah, I can find it. looks like this. Where can I put it? Enlarge this, put it over here. As you can see, this number over here, or well, this ratio, which was R over 2L and 1 over LC. So when you fill this into each other, you get something that looks like LC. Yes, I think that's correct. And you can see here oscillations, and it's becoming less resonant. Well, it becomes more damped, enters critically damped. I think that's 1. Yes, that's 1. This is critically damped, where it just follows this function. But as you can see, the resistance increases from here. 0.4, you can see peak current, but what you can also see is a negative current, because 0 is here. We get a negative current, which is very bad, because it will then charge the capacitor reverse, with reverse current, reverse voltage, and that's just not good, because you might blow up your capacitor. So this is the ideal state, what we want, or at least this number should be greater or equal than 1, but it's a pretty hard thing to do, because all these components have to line up with each other, and you can't simply you can't choose this or this. You can only influence C, and this are your design parameters, such as wire length, rail width, such as that, projectile design. So let's put this in a SPICE model and see if what we thought would happen actually does happen. So before we can actually model the inductor with it, we must determine the inductance of the rails. And as you can see, I found a formula on the internet for rectangular connectors or conductors, which are usually traces on PCBs, which are rectangular in form. So we have the length. If I model the rails, I lost it. Okay, if I model the rails, something like that. And then we have the length, we have the width, and we have the thickness, which is just the thickness of the tray, so I assume they mean the height. And if we fill this in as L to be 10 centimeters, you might think that's very small, but you saw how small the time constant was and how fast the projectile is done accelerating, so no need for long rails. And you will see that this will actually destroy your railgun if you have too long of rails. The width then to be, let's say, 3 centimeters, and the height also 3 centimeters. And if I fill this in the calculator, I get an inductance of 36 nanohenries, but this is only one side. We also have the return line, and we have a projectile in here. So this is times 2, and let's assume this. I'm not going to model a rectangular rails, of course, because as I said, no square parts. But the length will be about 1.2 centimeters, the width in 1 centimeters, and thickness also, which is 2.5 nanohenries. So this all adds up to be 72 plus 2.5 is 74.5. 74.5, I think. So that's very good actually. I have seen cases where it can get way worse than this, and we'll show you one of those. But first, let me show you the SPICE model. So I'm back in the SPICE model, and let's make room for the inductor. And the parameter will be of 75. How much was it? 74.5 nanohenries. So let's add this and let's run it. Let's see what we get in current. Of course, a much better curve, as you can see. It's no longer wait a second. There's also a series resistance in here, which should not be there. Let's put it at 0 ohms. You can see the current already increased. And as you can see, the slope is way better than before. If I can zoom only on this part, put a cursor in it. You can also see that the current has decreased because of the critically damped. I don't even think this is critically damped. You can plug it in. I don't think it is. I think it's over damped a little bit, just a little bit. But the slope is much better now. It's about 10 to the 9th. So that is, I think that's gigaamps. Yeah, that's gigaamps, no longer exaamps. So that can mean that we have a better representation of what's happening. And I'm going to copy this curve and show you, I'll show you what the waveforms are that I calculated. But let's see what happens if we increase series resistance. For example, if we make rails that are too long, if we use wires, and what happens if we make the projectile too bad, simply wires and such too long of rails. That will greatly influence, so let's put a factor 10 in the series resistance. You can see it's already decreased to 6.6 kiloamps, which is nothing what we had previously, but that's because we added a factor 10 to it. But what if we increase the inductance? Let's say we have rails of about half a meter or 15 centimeters. The width, well, half a centimeter. I've seen those. And the thickness also half centimeter. And we have an inductance of 510 nanohenries times 2 is 1020 nanohenries. And maybe put this even lower, let's say 10 milli. You can already see it's starting to go in the negative amps. Which is not good. Maybe we have a smaller bank of 2.4, well, 10,000 microfarads. You can already see the slope is going even more negative now. We get more oscillation. And if we look at the capacitor voltage, instead, what do we see? We see a negative voltage of almost minus 70 volts. Perhaps that's a blown up capacitor. Perhaps you just saved yourself, maybe. But what you can take from this is that it's not healthy for the capacitor at all. Because let me see how long it stays in the negative voltage range. For about 300 milliseconds. Hold on, wait, maybe I see now I looked at the wrong value before, so maybe I was right after all regarding the 3 times second time constants. Let me see, I said 400, about 400. Or maybe it was a little bit too much, the 3 time constants. So let's say 4 time constants, which was 24 times 4 is 5.7. Yeah, that's maybe more. So as you can see, it actually does do its job pretty well. So I just put the cursors in the wrong place, or I looked at the wrong place. But it doesn't matter now because we moved forward. Let me add the inductor back. So you can see how crucial it is to design your inductance properly, not rails too long, not too short. And I can even show you where I found the inductance, which this is not complete yet. I I said it was, for my part, was 10 centimeters, 1 centimeter, 3 and 3. So it was 3 times 3 times 10, and that gave me 74 times. That was 74.5 nanos plus an additional inductance, which I haven't talked about yet, and I will show now. So I found this PDF on the internet of my capacitor, and it's 3900 microfarads, and as you can see, it displays a couple of values, one of which is the size, the phase angle, the ripple current, the ESR, the impedance, and the equivalent series inductance, and it's about 22 nanohenries, and I have 6 of them in parallel, which should decrease 22 divided by 6 to 3.6 nanohenries. So I'll put that into my calculation here. 3.6 nanos, which will make a better model of what my real values would be. So we are about 50 kiloamps and 6 milliohms of resistance. It may look a little bit disappointing, because without the inductance we would have without the inductance almost 66.6 kiloamps. Now we only have, and as you can see, we only have 50 kiloamps now. But this value is so small. How could it have any impact like that so much? Well, as you can see, it's very important, even if it is so small. And I think the reason here is that the capacitor bank is even too little. I'm not sure what happens if I increase it. Yes, the current slightly increases, but not by too much. And this is more critically damped, I think, as it is with this. Now it's about the same. But I'll take a look at when it starts to oscillate. I don't think it will for a very long time. Now you can see I'm already I would have 18 capacitors to only have this little increase. So now we hear very fast discharge, and you can see the current is high, still high, and over the area. That's what I'm going to talk about next, is current distribution. I'm not sure if I will do it now or in another part, but you see that adding inductance, the stray inductance of rails, is extremely important. Maybe you can think of anyone that would not have thought about this and made his rails way too long, his projectile way too thick, or even too long in diameter, it only adds weight. Maybe they're using cables. Cables even have a higher inductance. Maybe you've seen some of these models on YouTube. I have, certainly. And you can now tell them why it's bad, what they did. Maybe even show them this video. And to be honest, this inductance is a function of distance. So let me show you again. Right here. So if we have this, we have length L. This is just a side view. Then the length in this equation can be replaced by x. It's a function of distance as it travels down the rail. But in addition, you will most likely, I will even most likely not even reach this 10 centimeters. So there's no need for half a meter long rails or even 1 meter, because it adds weight. You need more supporting structure. You need a longer railgun. Basically not worth it. So what I'm going to do is I make small rails, and the rest will be guidance. For example, it will be rifling, maybe stabilization, because that's a big issue, I think. And it will keep overall rail resistance down, because as we all know, it's R times rho over L over A, I think it was. So as this increases, resistance increases. It's bad. Small rails, small, tiny, very long rails, very bad. This only goes down, this goes even more up. So this goes even more up. As you can see, if I show you in the previous, not sure where it was. Yeah, it's right here. Then RS increases to maybe 12, maybe double it. Very here. Even lower current. Not good. So, I hope you've learned something from this video. I think you have, certainly. And I have also learned something. As I said, I only came across this last week or a couple of days ago. And that only shows you that you should do more research into this kind of stuff before you start building anything. Because if I wouldn't have known, I probably would have done something bad, and I would have wasted money to build something that's not up to its capabilities. And now I know what not to do. Maybe you can share this video with those kind of people who don't know. Maybe you don't even know, and now you do, so that's a good thing at least. And now you can increase the effectivity of your design and make it better than it would be. And I hope you also enjoyed this video, because otherwise this would be just a boring lecture. I hope it wasn't. And I'll talk about... what would I talk about? I'm not sure. I'm going to rewatch it and see what I was talking about. And I will do that in the next video. And I'll see you then. Thanks for watching.